Hello, everyone. I am Shiyi, a CS Master student from ETH Zurich. I'm going to present our recent paper, Accelerating Data Serialization and Deserialization Protocols with In-Network Compute. I will start with a brief introduction on our motivations and contributions. In the second section, I will explain some background knowledge, illustrating in detail what is data deserialization, why is it expensive, and then what kind of specialties are needed by SmartNICs to offload deserialization tasks. At last, I will illustrate how exactly the tasks are offloaded, and then I will demonstrate the evaluation results. An important use case for data serialization deserialization protocols is for remote procedure calls in microservices. The microservice architecture consists of fine-grained modular software components interconnected through RPCs. As shown in this figure, different microservices are often written in different languages with their own data format. Therefore, to ensure interoperability between each communication pair of microservices, we will need an intermediate data transformation layer to convert data back and forth between microservices. Frameworks like Google's protocol buffers and Apache Swift provide applications with the ability to exchange all kinds of structured data in a language and architecture-independent manner. Normally, when two applications want to communicate with each other, say one wants to send a message to the other, on the sender side, the structured messages will be flattened, serialized from the in-memory representation to the wire representation. Then, on the receiver side, the wire representation will be deserialized back to the in-memory representation. However, such process is expensive. Prior works have shown that around 5% of CPU cycles in Google's data centers were spent on protocol buffers. In 2020, Facebook also reported an average of 6% of CPU cycles that were consumed by data serialization and deserialization across 7 key microservices in their fleet. Therefore, it is important for us to find a way to free up CPU cycles from this data transformation overhead and make them focus on the core application logics. In this paper, we investigate how in-network compute can accelerate SerDes activities by processing data on a per-packet basis. Our contributions are as follows. First, we demonstrate how data deserialization can be offloaded to fully programmable SmartNICs without modifying its original semantics, addressing the challenge of transferring and manipulating complex pointer-based data structures between different memory spaces. Second, we show how our approach can free up CPU cycles by pipelining the deserialization and the execution of the main application logics. Third, we also identify and discuss SmartNIC specialties that are needed to offload the SerDes activities. Here, we also sketch an overview of possible data deserialization strategies to give you a high-level idea of in-net SerDes. The first figure shows a case of CPU-based deserialization. Serialized requests are received by the NIC and written to the host memory, either passing packets to the operating system network stack or using remote direct memory access. The host CPU will read the serialized data, deserialize it, and write the result back to the main memory. The second figure shows a case where deserialization is offloaded to a near-core specialized accelerator. Incoming data is written to the host memory. After that, the specialized hardware accelerator is instructed by the host CPU to perform the deserialization. In this case, the hardware accelerator reads data from the host memory, deserializes it, and writes a result back to the host memory. Finally, the last figure shows our approach. Incoming data is processed directly in the NIC, where the data deserialization process is executed. The deserialized data is written directly to the host memory without intermediate copies or host CPU intervention. Have known our motivations and contributions. Next, we move to the background section, and we will first introduce in detail what is data serialization and deserialization. Now we will use protocol buffers as an example to explain how data SerDes protocols internally works. and why we want to offload them. A protobuf message is a collection of fields. In the protobuf schema, each message field has a field data type, a field name, a field number, and potential qualifiers, including optional, required, and repeated. For example, in message student, the first field has a name ID with data type UIN64 and the field ID to be 1. A field can also be a user-defined message type, which allows for messages to contain sub-messages, and we call this embedded messages. For example, in a message student, we have advisor as embedded messages, and this field is labeled as repeated, which means a student has multiple advisors. On the wire, protobuf messages appear as a sequence of bytes containing a set of key value pairs that represent fields in the messages. Here, the key is a variant encoded version of the field number concatenated with a 3-bit wire type. Then, what is a wire type? Different data type for field will yield different wire types, which decide how the field will be encoded to the wire format. There are three wire types that are heavily used: var-int, length delimited, and fixed length types. For the var-int type, an integer will be encoded into variable length, dependent on its value. As shown in this figure, the most significant bit of each byte of a var-int indicates whether it is a last byte of the integer or not. The remaining bits are part of the actual value of the integer. Therefore, to decode a var-int, we need to check for every byte whether this is a last byte and do bitwise operations to calculate our original integer value. For length delimited type, the value part first contains var-int encoded length in bytes, representing either the length of a string or the length of a sub-message. Then it contains the actual data of the field. For fixed length type, the values are just directly copied to or from the wire format. Normally, these protocols are not self-describing and requires non-trivial sequential processing for deserialization, which makes them different from the MPI-derived data types, where a data type fully specifies a message. As mentioned before, the var-int encoding is heavily used for encoding not only the integer values, but also the field keys and field lengths. Here we have an example for var-int decoding. For each byte, we will perform a branch to check the most significant bit. If it is 1, it means we have more bytes to read. We will perform bitwise operation to isolate the remaining 7 bits and write them to the output buffer, and then repeatedly do the same for the following bytes. Such chain-style decoding will result in data-dependent branch per byte and many dynamic instructions that can limit the transformation throughput. In our paper, we mainly focus on the deserialization part, as deserialization is more complex for additional 2 reasons. First, deserialization is hard to be parallelized and is inherently a serial process. Just look at the example here. We cannot actually know the start position of the second field unless we have decoded the first field, while serialization, on the other hand, has more opportunities for parallelism. Second, deserialization requires excessive memory allocation and memory copy when converting the data from the wire format back to the in-memory pointer-based architecture structure. And now I will introduce some of the basics for in-network compute. To make deserialization offloading effective, our solution should satisfy 2 requirements. First, be available to user-level applications, and second, be flexible in terms of expressing the offloaded tasks. User-level applications should be able to offload tasks without requiring elevated privileges. For example, a user-level application should be able to define tasks to be offloaded to the network without violating isolation principles. This requirement also enables application to express different SerDes protocols without the need to stick to a limited set of them. This requirement is not satisfied, however, by many in-network compute solutions like DPDK, where tasks are defined at the system level and not at an application level. Moreover, as we have demonstrated before, the deserialization tasks can be complex and they are dependent on the specific SerDes protocols. In network compute solutions like eBPF and Portals 4 impose constraints on the code describing the offloaded task, or only allow the offloading of specific operations, making them not flexible. And in network compute solution that satisfies these requirements is SPIN. With SPIN, user-level applications can express per-packet tasks to be offloaded to the NIC. These tasks can be expressed in C or C++ or any other languages that the specific SPIN implementation has compiler support for, which is very similar to writing CUDA programs for GPUs. Applications define packet handlers to be executed on the NIC. These handlers are associated with classes of messages and are triggered and executed as packets arrive from the network. An application defines an execution context that includes information such as pointers to the packet handler functions in NIC memory, and NIC memory previously allocated by the application and used by the handler to share states. This execution context is then associated with a message or packet. The NIC is in charge of matching packets to execution context and then triggering the respective packet handlers. In this paper, we use PsPIN and implementation of SPIN based on the POP framework. Now let's take a look at how the deserialization tasks are offloaded with SPIN. As mentioned before, protocols like protobuf are not self-describing. Therefore, the first thing we need to do is to install message descriptors onto the NIC. Note that message descriptors are also hierarchical pointer-based data structures. Therefore, we need to first flatten them and write them to the NIC's memory with an array indicating the offset of each descriptors. Packets are then received and deserialized by the HPUs in the NIC using the descriptors indicated by the RPC method types. The decoded contents of the message will then be written directly to the host memory through the DMA engine. Then I will briefly introduce how the host and NIC memory are managed. The host is responsible for providing enough memory to be used by the NIC. It allocates buffers in host memory and transfers the ownership to the NIC. This pinned memory region is further split into disjoint regions that are assigned to each cluster. We have at the very beginning of each cluster's L1 scratchpad memory some bookkeeping information for managing its own partition of the pinned memory. Note that this part is quite similar to allocate host memory in CUDA programming. On the NIC, each cluster has its own L1 scratchpad memory. We reserve some regions at the beginning of each cluster scratchpad memory to cache the message descriptors. Then we further assign each HPU in the cluster a disjoint partition of the remaining scratchpad memory. The overall deserialization logic is similar to the original protocol. Typically, the most challenging thing for offloading deserialization to accelerators that do not share the same memory space with a host is rewriting the pointers to reference host memory space. For this reason, most of the current works try to avoid this challenge either by using on-chip NICs or putting accelerators near core. Instead, our approach directly addresses it, thanks to the fully programmability of SPIN. In general, we replace the typical malloc and memcopy logic with allocate host memory and DMA to host logic in deserialization. Now we will illustrate our deserialization methodology through some examples. We first look at a simple message which only contains a single string field. The upper figure shows real byte stream of this message. The figure below demonstrates the decoding process in the NIC and how data are moved across NIC and host memory. Here, the blue square is a field header corresponding to the keys in the key value pairs of the byte stream. The red square is the var-int decoded field length. The green square is a message header which contains some metadata for the message. On the NIC, we have the payload stored in NIC's L1 packet buffer, and the intermediate data structures, like pointers to strings or pointers to sub-messages during decoding, are temporarily kept in NIC's L1 scratchpad memory. To decode such a byte stream, as shown in this example, we first decode the field header, which tells us that this field is of type wire type length delimited. We then decode the length var int and allocate some memory on the pinned host memory according to the decoded length. Then in step 1, we can use a DMA engine to write this string data directly from NIC's L1 packet memory to the allocated host memory. And the pointer here is then naturally referencing the host memory. Finally, in step 2, we write the top-level message M to the host. Then let's look at the more complex message, which contains an embedded message. Since embedded messages are also of wire type length delimited, to decode M3, we need first decode the field header and length, and then we know the following bytes construct a message of M2. So we can call the decoding function recursively to decode M2. We can regard our L1 scratchpad memory as a kind of stack for storing some intermediate pointers during decoding. The stack grows when we enter the decoding function for an embedded field and moves back when exiting the function. The decoding of M2 is the same as we have done in the previous example, and the host address to which the submessage M2 is written to is stored in the corresponding pointers in M3. After all, the fields of M3 are decoded. We write M3 to the host. At last, we will look at the message M1, which contains repeated embedded messages. To start, in step 1, we first decode the first field, the uint64 field, and keep the value in the corresponding field in L1 memory. We go on scanning the packets and record how many times the M2 is repeated. Knowing the quantifier of the repeated field is 2. In step 2, we set the quantifier for the repeated field to be 2. In step 3, we allocate an array of M2 pointers in L1 memory accordingly, and record start address of the array in M2 vector pointer. For the decoding of the first M2, we follow a similar procedure described in the embedded message case. In step 4, we decode M2, allocate the host memory for M2 string field, write the string directly to the host memory. In step 5, we allocate host memory, write M2 to the host, and set a corresponding pointer with a host address in step 6. We then just repeat these procedures for other M2s. At last, after all the fields are decoded, in step 7, we allocate host memory for the array of M2 pointers, write them to the host, and in step 8, we reset M2 vector pointer with host address 3. And in the final step, we allocate the host memory and then write the M1 message to the host. So now I will show some of our evaluation results. Similar as done in previous works, we extract 5 most representative RPC requests from the desk star bench, composing 3 typical services into these various kinds of microservices. These 5 RPC methods composing the 3 services vary in several aspects that can significantly influence the deserialization throughput. First, number and computation of fields. And second, the depth of the nested messages. And third, whether the message contains long strings or bytes. For example, in the user service here, which contains 2 RPC methods, and methods in this class of service are composed of basic type of fields, integers and strings, and do not contain embedded and repeated fields. As these requests normally do not carry long strings, they have relatively higher deserialization overhead per byte. And other services here are different in terms of these varying factors, resulting in different deserialization overhead per byte. For our approach, all the tests are performed on spin through cycle-accurate simulations with a PsPIN toolchain, and we simulate a 400 gigabits per second network. In the microservices benchmarking tests, we compare our approach with decoding directly on AMD Ryzen 7 CPUs. For microservices benchmarking experiments, we will report results for two modes. First, a single services, and second, mixed services. In single services mode, for each service, different types of RPC requests it contains will occur with the same probability. In mixed service mode, all types of RPC requests will occur with the same probability. This figure shows the throughput of achieved by PsPIN and the CPU for deserialization requests belonging to different services. The CPU case models an ideal CPU-based deserialization where all requests are available in host memory. The CPU is only used for deserialization tasks and no contention or other overheads are experienced. For each service, we will report first the PsPIN throughput and second, the PsPIN goodput, which is a throughput of PsPIN without considering packet header overhead. And third, the single core CPU throughput, and fourth, an extrapolation of the CPU performance when 8 cores are all used for deserialization. In all modes, PsPIN-based deserialization is consistently faster than a single core CPU-based one. And on average, PsPIN can achieve 4.8 times higher throughput than a single CPU as shown in this figure. But if we consider multi-core deserialization, then we see how the CPU outperforms PsPIN. Well, this is expected due to the compute-intensive nature of deserialization. It is worth noting that the CPU-based results represent a speed-of-light scenario, where all cores are dedicated to data deserialization and none to the execution of the actual microservices. To gain a better understanding of the impact of deserialization offloading to the NIC, we show in this figure an analysis of the overall microservice throughput as a function of the microservice time. Dedicating all 8 cores to the deserialization process results in better overall throughput than PsPIN. However, in reality, the CPU cores are used for not only deserialization tasks, but also the core application tasks. As we can see, as a microservice running time increases, the CPU-based case, the deserialization overhead impacts the microservice throughput, as deserialization and microservices are serially executed, and there will be resource contention between core application logic and data deserialization tasks. Instead, with PsPIN, these two activities are well pipelined, resulting in better performance. Finally, as the microservice time increases, the microservice execution itself becomes a bottleneck, causing the performance convergence of the two approaches. To conclude, for short-running microservices, offloading the deserialization tasks to SmartNICs can achieve up to 60% throughput improvement, according to our modeling. In conclusion, most of existing works co-design software and hardware to accelerate data SerDes. Our approach is fully expressed in software, which can be easily extended to support new protocol versions or variations. We also addresses the challenge of transferring and manipulating complex pointer-based data structures between different memory spaces, which has been avoided in existing works by placing the accelerator either near core or using on-chip NIC. And unlike other NIC-based works that propose new SerDes protocols, for example, leveraging NIC scatter and gather features, we keep the original protocol semantics. We also discuss about the wanted SmartNIC specialties needed for offloading the data deserialization tasks. And our microservice throughput modeling shows that for some short-running microservices, we can achieve up to 60% throughput improvement by pipelining data deserialization and actual application tasks.